We are doing 13.3 special right triangles, and this one's kind of funny because the whole point of doing special right triangles is it allows us to skip ahead and kind of find some shortcuts for trig actually, so we don't have to use as much trig or set up the those baseline trig equations. And I'll show you what I mean here in a second. So the first special right triangle is an isosceles right triangle. If you don't want to try and solve this, just hang on the line. We'll skip ahead. If you do want to try and solve this, pause and see if you can figure it out. The other one we may want to solve for is an equilateral right triangle. This one, ABD, is the equilateral triangle. So all these angles would be equal, all the side lengths would be equal, and then the altitude is given here as well. So it's kind of cut in half. BC, therefore, goes right through the middle. So just focus on the half here and see if you can figure out all of the angles and side lengths for this, this left half triangle. Again, pause here if you want to try and figure it out on your own. Okay, so the answers, as it turns out, are that if we have this unknown side length here, then this hypotenuse is whatever that side length is times the square root of 2. And it's a 45, 45, 90 triangle. Hope you guys figured that one out. This one over here, the angle is 60 and half of 60, which is 30. So this one's called a 60, or 30, 60, 90 usually. And then this side here is half of one of the equilateral triangles sides. So this side is twice the short one. For some reason they use the short one as the reference, and that's fine. So if this is x, this long one is twice that, and then the altitude here is, or the long leg is x times the square root of 3. You should have been able to figure this out using Pythagorean theorem, but if not, just use these two examples for a lot of the homework. So again, we can just shortcut ahead here, and I'll show you what we have. So if we were to find the unknown side lengths of this 45, 45, 90 triangle, before we would have to use some kind of trig involved, right? We'd have to, or at least Pythagorean theorem, and have a couple like x here and x there, and then try and solve for x, and it would be a big pain. Lots of algebra. Here, though, we can do something a little simpler. We just need to figure out what number times the square root of 2 gives 10, right? So 10 is equal to AC times the square root of 2. So AC is our unknown variable here. And this is actually pretty tricky if you're not very good at working with square roots. So let me break down this, let me factor this 10 real quick. So 10 we can factor into, say, 5 and 2, right? 2 times 5. But we can factor this 2 even further if you think about it. What two numbers multiply together to give 2? Well, 1 and 2 do, sure, but we can also use the square root of 2, right? Square root of 2 times the square root of 2 times 5 equals 10. And so if we set up our algebra equation with this instead of 10, it becomes pretty clear how we get this answer. We have square root of 2 times the square root of 2 times 5. This is our 10, right? The hypotenuse is equal to AC. We'll just put AC, but an unknown, right? Could put x. AC times the square root of 2. So now if we were to solve for our unknown, we simply divide both sides by the square root of 2. Divide by square root of 2. These guys cancel, and we're left with our unknown is 5 times the square root of 2. So that's where that number comes from. Don't worry too much about the square roots. If you always ever get into trouble, you can always just turn them into decimals. I'll accept it either way. However, there may be, say, multiple choice answers given in square root form or something like that. So it's good to be able to use square roots, and you will probably have to use them in future math classes as well. So this guy here in right triangle DEF, D is 30, E is 60. The shorter leg here is 5 times the square root of 3. And let's go back here and look at the relationship real quick. This short side we're going to call x. That means the long leg is going to be x times the square root of 3, and the hypotenuse is twice that. So let's figure out, we need to figure out both these side lengths. Well, the easy one is going to be df, right? It's simply twice ef. And so what is 2 times 5 times the square root of 3? Well, that's 10 square root of 3. It gets a little harder when we have to find dE. We know that dE is EF times the square root of 3. So we have to multiply the square root of 3, so that's a little hard to see there. So what is 5 times the square root of 3 times the square root of 3? Well, the square root of 3 times the square root of 3 is 3, right? So that's 5 times 3, or 15. So give yourself a pat on the back if you're able to figure that one out. Here's another one. Go ahead and I'll pause so you can do 5 and 6 real quick. Oops. Okay. So for number 5 here, it's a 30, 60, 90. So again, some unknown times the square root of 3 gives us 4 square root of 3. So the unknown, wait, how did I mess that up? Oh yeah, it's twice that. Yeah, so 1/2 of 4 square root 3 is 2 square root 3. Yep. And then which gives us this, and then 2 square root of 3 times the square root of 3 gives us 6. This guy over here, we know that this side is 2 times the square root of 6. What is 2 times the square root of 6 times the square root of 2? Right? That's the hard question. 2 times the square root of 6 times the square root of 2. When we are multiplying square roots, we can multiply what's inside, right? So the square root of 6 times the square root of 2 is equal to the square root of 12. And the square root of 12 can be factored into 2 times the square root of 3. So that's how we end up with 4 here. We also just want to touch on real quick, I'll just give you the table for all the trigonometric ratios here. For example, if I were to look at this 45, 45, 90, right triangle, the ratios here for one of these 45-degree angles, it doesn't matter because they're both equal, are right here. Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent. So therefore they just plug in the values. It's a little weird. They came up with square root of 2 over 2 as opposed to 1 over the square root of 2, but I don't know why they did this. I would have put 1 over the square root of 2. But as we all know, with a fraction, you're allowed to just multiply both the top and bottom by something. So for some reason, they multiplied this by square root of 2 over square root of 2, which gave them the square root of 2 over square root of 2 times square root of 2, which is 2. This is a slightly more useful because then the denominator is a whole number, I guess. For this one here, I want you to pause, see if you can figure it out. If you can't, fill out these things. If you need help, just move ahead and copy it down. That's okay too. So here are our values for the sine, cosine, and tangent, and sine, cosine, and tangent of both 30 degrees and 60 degrees. Again, you could plug these into your calculator to figure these out. Some of you guys have fancy calculators that actually give square root answers, and that's pretty cool. But be aware that you may need to use this table if you need an answer in square root form, because they're pretty hard to derive otherwise. A few other things. We've come across Pythagorean triples in our class before. Most often, though, we've probably ran into this one a dozen times or so, is the 3, 4, 5 triangle. This 3, 4, 5 triangle, right? 3, 4, 5. So if A here is 3, B is 4, we know that 9 plus 16 is 25. The square root of 25 is 5. So that gives us our 3, 4, 5 triangle. There's a few other, so there's an infinitely number, but there's a few other that have small enough integer values to be useful. And that's 5, 12, and 13. I think we had this on one or two homework problems, and I haven't seen these other ones ever, so just ignore those. But really just, you should know the 3, 4, 5 triangle. We'll watch this video in class maybe. And with that 3, 4, 5 triangle, it doesn't always have to be side lengths of 3, 4, and 5. It can be any scale factor version of that, right? So we can multiply each of those by 2 or multiply them each by 3 or something like that. We'll look at this example real quick. This is a 3, 4, 5 triangle, but what is the scale factor, right? Most of you guys can probably pretty quickly figure out that if this is the short leg, that's going to be the 3, this is going to be the 4. So what number times 3 equals 18? Does that same number times 4 equal 24? Yes. So therefore, PR is 5 times that same scale factor. And the scale factor is, of course, 6. So therefore, PR equals 30. Mostly, this is a shortcut method. Again, you could crank this out with Pythagorean theorem. But you can save yourself some time and some effort and brain power if you can just recognize this pattern and use it. So this is going to be our last lesson in this section. We're going to save 13.4 for the next module. So we're just going to kind of push it back onto the next module and deal with it there. So last lesson before we do a chapter test. Thanks.